Ntanị gafe preaching on yele. My wife special class.
Let's go to this thing. Make sure what is happening in the class. But we also need to close this one because because it's like we are broadcasting. So we need to close.
Zoom. What is me? Swimmer. Bring the colony. Zoom colony. There's nothing that epsilon. Yeah. Good morning, students. In our first lecture, my attention was pointed to a particular variable, pressure, that we said was an extensive property. So pressure is an intensive property because it is force divided by area. Force is intensive and area is extensive. So on the whole, pressure is an intensive property, not an extensive property. From there, we move on to our week 4 lectures. And that'll be slide 38, which is on what is titled Thermodynamics and Equilibrium System. Now, the first law of thermodynamics, like I told you the other time when we had our last lecture, that what the law is really telling us is that the total energy of an isolated system is constant. So we're moving ahead from there, and we are going to start from this. And it's stated mathematically in terms of internal energy, heat and work. The law of conservation of energy is referred to as the first law of thermodynamics. First law of thermodynamics. And what it is saying is that the change in internal system of the internal energy of the system is equal to the change, or is equal to the heat energy of the system plus the quantity of energy transferred by doing work on the system. So in this equation, the Q system is the quantity of energy transferred by heating the system Please note that again. The Q system is the quantity of energy transferred by heating the system. And W system is the quantity of energy transferred by doing work on the system. Then there are also other things that we need to note is that all these thermodynamic quantities, they have magnitude and they also have signs. They have magnitude, they have sign. So, and then therefore, we are going to look at the sign convention. We look at that, the sign conventions. And what it's saying is that if heat is transferred into the system from the surroundings, then Q is assigned a positive sign. That is, it is plus Q, which means that heat has been transferred into the system from the surroundings. And if heat is transferred out of the system to the surroundings, then Q is assigned a negative sign, which is minus Q. And that shows that heat has been transferred out of the system to the surroundings. In the same vein, plus W means work done on the system. Work done on the system. So if work is done on the system by the surroundings, then W is assigned a positive sign, plus W. And conversely, if work is done by the system on the surroundings, then W is assigned a negative sign, minus W. Please let us note all these signs because it will help us in our calculations. It will help us in our calculations. For example, now, look at example 2. A gas absorbs 35 joules of heat and does 15 joules of work. What is the change in internal energy? And from our equation, we know that delta E equals Q plus W. So our Q is plus 35 joules. And the W, the work, because you need to understand that, say a gas absorbs 35 joules of heat and does 15 joules of work. That means the system is now doing some work on the surroundings. Therefore, the W will be negative, that will be minus 15 joules. So when you now add the two together, if you are adding 35 joules to minus 15 joules, it gives you 20 joules. That one should be clear enough. I will repeat it again so that you can have a very firm understanding of what we are saying. Look at the question again. A gas absorbs 35 joules of heat and does 15 joules of work. What is delta E? What is the change in internal energy? Remember, I told you the symbol for internal energy could be U or could also be E. Here we are using E. So, and we know that from our equation, our change in internal energy will be heat plus work done. And now we have delta E equals Q plus W. Our Q is positive here, and our W is negative. A gas absorbs 35 joules of heat and does 15 joules of work. So if you are adding the two together, we now have plus 35 joules. We add it to minus 15 joules, and that gives us 20 joules. Now we're moving to another subtopic, expansion work or pressure volume work. Like I told you the other time, the major thing we'll be looking at in this thermochemistry is that we'll be looking at pressure volume work. That is, whether by expansion or by compression. So in our elementary thermodynamics, the only type of work that we'll be considering will be work done in expansion or work done in a compression of a gas. Now, assuming you have a cylinder, if you have a cylinder, the pressure inside is the P in, not the internal pressure. Then the one outside the piston is the PX, So that is the external pressure. So, and then we need to make some assumptions. So we are making an assumption that our external pressure is greater than internal pressure. And that shows to you, if external pressure is greater than that of internal pressure, then that means we are looking at we are looking at a kind of a compression. And if there must be an expansion, then the internal pressure would try to push the piston upward. So therefore, from our assumption, PS is greater than PE. And we know that from our definition of work is work equals force times a distance. As if W equals F times L, let's say length. And then we also know that pressure is force over area. And also from there, if we make our force the subject of the formula, then we know that our force equals the external pressure times area. Let's move ahead. The area represents the cross-sectional area of the piston. Therefore, we know that W now equals PX times A times L equals, since we know that force is PX times A, and we know that our W is F times L. Therefore, substitute your PX times A into where you see F. So it gives us W, that gives us that our work equals PX times A times L, where A is equal to the area and L is like height or the length. And when you multiply area times height, you have volume. That's why you are having that delta V. I will repeat that again so that you can understand. From W equals PX times A times L. We have our PX there, it has not changed. But you have the area times the length, it gives you volume. So we now have W equals PX times the change in volume, where the delta V equals change in the volume of the gas. And since the gas is doing work on the surrounding, like I told you now, the gas now, which is inside, it has a lower pressure than the external pressure. So if you now be pushing the piston, therefore, if the system is doing work on the surrounding, then the sign there will be negative. So we have a negative sign. Therefore, our W now equals minus PX delta V. So this definition is for any change. So we need to know that this definition is for any change. When the volume expansion by the V against a pressure, so we have this. So because if you are having a volume expansion, that means something is happening to the pressure. The pressure will have to decrease. You are pushing it up. You are pushing it up because we want to expand the volume. And if you increase the volume, so if you increase the pressure, then you are reducing the volume. You need to know that from our elementary chemistry. So the volume expansion by the V against a pressure, PX, therefore the work that is done will be dW equals minus delta V. And you see that one as our equation 1. And if you want to obtain work that is done when the volume changes from maybe initial volume to the final volume, then we need to apply some elementary mathematics integration. We integrate the above equation. So between the initial and the final volume, so I think the boundary value will be between the VI and then the VF. And therefore you have W equals minus integral VF, so VI to VF, then PX delta V. Now I want to look at free expansion. When I say free expansion, that means there is no opposing force. If the volume wants to expand, it will just keep on expanding continuously. Nothing stops it. Therefore, it means our Px is 0. And no matter what the volume is, if you multiply it by 0, it gives you 0. Therefore, the work done by a free expansion equals 0. So the change in the work. So if you look at it now, the W equals 0 at every stage of expansion, because there is no change taking place. The reason is that the pressure, nothing is there. No, there's no barrier. Nothing is stopping it. It's not working against anything. Hence, for free expansion, our W equals 0. Let's look at another example. Let's look at another example. Calculate the pressure volume work done when a system containing gas expand from 1 liter to 2 liters. It's a constant external pressure of 10 atmosphere. Express your answer in calories and joules. So express your answer in calories and joules. Now, our work is very simple, since we already know that the work done will be minus Px, V2 minus P1. And we know that the volume, the pressure is 10 atmosphere. If you look at that question again, it said it expands. So let's go to that question again. Calculate the pressure volume work done by system when a system containing a gas expands from 1 liter to 2 liters against a constant external pressure of 10. So our pressure is 10 atmosphere. And the initial volume is 1 liter. The final volume, which is V2, is 2 liters. Therefore, our equation becomes minus Px into V2 minus V1. And that gives us the answer. And then if you are to convert the calorie to joules, we know that 1 calorie equals 4.184 joules. All you need to do is just to multiply. Now let's go over to reversible and irreversible process. Reversible and irreversible process. Reversible and irreversible process. Like we said in our first lecture, a reversible process can be halted at any stage and then revert by an infinitesimal modification of a variable. What we are saying is this: you can halt it you can stop it at any stage, and then you reverse it by a kind of minute modification, small modification of a variable. Because why is that what happening? It is because at every stage your system is at equilibrium. Therefore, any little change in any of the variables because a change, because the process to reverse. We call it a kind of reversible process. So in a reversible process, the system is at equilibrium at every stage of the process. And how do we achieve that? We can achieve that when we set our external pressure Px equal to P. That is the pressure of the gas that is confined. So what we are saying is that even the gas, so the pressure of the gas that is confined inside your cylinder, the pressure is now internal pressure. So we set the internal pressure and the external pressure to be equal to each other, thereby making the system to be in mechanical equilibrium with the surroundings by an infinitesimal change in the external pressure. And this could be in either direction. So what we are seeing is that our P in equals Px. Internal pressure equals external pressure. And then it means P in equals external pressure, then equals P. Because only one pressure will be defined for the system, which you need to know that for a reversible process, only one pressure would define it. Since we know that our internal pressure equals our external pressure. Therefore, our equation, record that equation 2 is W equals minus the integral of Px dV within the boundary value of V, initial volume and then final volume. So it becomes dW equals minus Px dV, which gives us minus P dV. Since already Px and P, we can now generalize it as P. So it equals minus P dV. That gives us our equation 3. Now, if you now want to calculate the total work done for a reversible expansion, then we can now say that W equals minus integral of P dV from initial volume to the final volume. That gives equation 4. That gives equation 4. So please note that. Note that. Then again, we want to look at our irreversible expansion. So this is just the opposite of our reversible expansion. It's the opposite of our reversible expansion. And in an irreversible expansion, the conditions, they are not as they are in reversible expansion. In an irreversible expansion, our internal pressure is greater than the external pressure. And that makes the process to be irreversible. And that shows that the system does not remain at equilibrium at every stage of the process. Which we need to note that. For an irreversible process, the system is not at equilibrium at every stage of the process. Therefore, the pressure volume work, when we want to calculate it, will be the W equals minus Px dV. Minus Px dV. That gives us our equation 5. By the time we'll be doing some examples, it will become very clear, to become clearer. So a reversible, we now want to look at expression for reversible expansion. Expression for reversible expansion. Now I want to look, 1, reversible expansion at constant pressure. Remember, we talked about isobaric, we talked about isochoric, and isodermal. Now we're looking at an expansion at constant pressure. The P equals 0. The P equals 0. That is, there is no gate that it is constant. And we also know that from expansion of reversible work done, we know that W equals minus P dV, integrating from V1 to V2. And if our pressure is constant, then we can take the pressure out of the integral sign. We take it out, so it becomes W equals minus P dV integrating from V1 to V2. And since P is constant, so even when you are integrating, it's not affected. So our P remains P. But you are now integrating the V from the initial volume to the final volume. So that gives you V2 minus V1. Hence, our W equals minus P into V2 minus V1. And then it gives us minus P change in volume. Minus P, then change in volume. change in volume. Then let us also look at expression for isothermal reversible expansion. Expression for isothermal reversible expansion. Expression for isothermal reversible expansion. When we say isothermal, we are saying is that the temperature also is constant, there is no change. So the T equals 0. Now we are starting from our equation. W equals minus P dV. And we're integrating from the initial volume to final volume. And now we know that the pressure is not constant. Please note this. In our former expression, we said the pressure was constant. But now in isothermal, pressure is not constant. And that shows that the pressure will be changing as the volume is changing. So it becomes a function of volume. And that's why you are going to see in equation 7 that W equals minus P V. So a function of volume, dV. So therefore, in order to integrate equation 7 now, we must know how our pressure is changing with volume. And for us to do that, we need to go to some of the things we had earlier learned. So from equation, so we go to the equation of state. And if our substance is a gas, we can get an approximate value of the expansion work done using the ideal gas equation. We know that our PV equals nRT. And from PV equals nRT, then P will be nRT over V. P will be nRT over V. Let's move ahead. Therefore, if we now put our equation 8 into equation 6, putting equation 8 into equation 6, so it gives us W equals minus nRT over V dV. Now integrate between V1 and V2, or initial volume and the final volume. But we know that what we are looking at is an isothermal expansion. And that tells us that our temperature is constant. So we know from these variables, temperature is constant. Our R is a universal gas constant. N is constant, is the number of moles. So we can bring our nRT outside the integral sign. And that gives us W equals minus RT, then integrating 1 over V dV from initial volume to final volume, which is V1, V2. I'll repeat that again. The T is constant because we are considering an isothermal expansion. The T is constant. We are looking at an isothermal expansion. Therefore, the nRT can be brought outside the integral sign, giving us W equals minus nRT, then integrating 1 over V dV from initial volume V1 to V2. And from there, we will obtain minus nRT, the natural log of V2 minus V1. And you know the law of logarithm. If you are subtracting, it becomes W equals minus RT, the natural log of V2 over V1. That gives us equation 11. Equation 11. And from our gas laws, we know that P1 V1 equals P2 V2. But in equation 11, we have V2 over V1. That is, we have minus nRT, the natural log of V2 over V1. So we cannot substitute and put where we see V2 over V1, we put P1 over V2. Please, I will repeat that again. I'll repeat that again. If you integrate 1 over V, it gives you the log of V. And since our V is between the initial and the final, so the V there will now be V2 minus V1. So we now have W equals minus nRT, natural log into V2 minus V1. And applying the law of logarithm, you now have minus nRT, the log of V2 divided by V1. That gives equation 11. And from our gas laws, we know that P1 V1 equals P2 V2, which gives V2 over V1 equals P1 over V2. And since we have V2 over V1 in equation 11, then we cannot substitute it with P1 over V2. Therefore, in terms of pressure, we can, in that equation, in that equation 11, we have gotten the work done in an isothermal expansion in terms of volume. You know, we said that the pressure is changing as the volume is changing. We are looking at the reaction of pressure to the change in volume. So now we are getting it now in terms of volume in equation 11. Now in equation 12, since we have now substituted our V2 over V1 with a P1 over P2, we now have minus W equals minus nRT, the log of P1 over P2. So now we have got it now in terms of pressure, both in the initial and then final pressure. And we can now change it to our logarithm 10, and that gives minus 2.303 nRT log P1 over P2. Log P1 over P2. Log P1 over P2. Please, you need to note that, maybe let me show you that when you have the natural log of X, it gives you 2.303, the 2.03 log X to base 10. So we are going to the next slide. The isothermal irreversible expansion work. Isothermal irreversible expansion work. So for an ideal gas contained in a cylinder with a piston, the process of expansion of the gas is performed irreversibly. So, and this makes the system, it makes it to drop instantaneously. It drops suddenly. Immediately, there is a change, the thing drops. So that's not dropping of the external pressure to final pressure. It's no longer reversible, it is irreversible. So it moves from the initial to the final pressure. So therefore, the work done is now again the pressure throughout the whole expansion, and it is given by W equals minus external pressure. Then if you integrate the V from the initial volume of V1 to V2, and since we're integrating this, it becomes minus P2, then V2 minus V1, or our PX into V2 minus V1. Already the pressure has dropped, the external pressure has dropped from what is used up to as PX, it has now dropped to the final pressure, which is P2. That's why you have your P2 there. P2 into V2 minus V1. And that gives the final pressure, then the change in volume. Change in volume. The change in volume. Now let's look at this equation. Let's look at this equation. Sorry, the example. Let's look at this example. He said 1 mole of an ideal gas at 25 phase change. 1 mole of an ideal gas at 25 degrees Celsius is allowed to expand reversibly at constant temperature from a volume of 10 liters to 20 liters. Calculate the work done by the gas in joules and the calories. In joules and the calories. So you will see this one there, where you have this equation. Now we look at our V2. Then we also know our V1. The V2 is 20 liters. The V1 is 10 liters. We know our temperature. We know the temperature, which is 298 degrees Celsius. Then we also know that the number of mole is 1. We put that one there. And also know that our R equals 8.31 for joules per mole per Kelvin. So you just do your calculation. And if you get it in joules, and then you can also convert it to calories. If you divide by 4.184 joules, 4.184 joules. And like I told you, your natural log X equals 2.303 the log X. Log X. So let's take this one. Let me see. We have several examples. I will take one more example. Then I will allow you to study the other examples and understand it on your own. Then we'll meet next class. But let us look at example 2. Let's look at another example. Example 3. Find the work done when 1 mole of the gas. Find the work done when 1 mole of the gas is expanded reversibly, and isothermally from 5 atmosphere to 10 atmosphere at 25 degrees Celsius. Can you see? So instead of you having a volume now, you are having pressure. So all you need to do now is for you to be able to record all the former equations that we derive. And that gives you W equals minus nRT, the natural log of P1 over P2. We know what N is. N is 1 mole. Say when 1 mole, N is 1. We know what our R is, 8.314. Then at 25 degrees, that is 298 degrees Kelvin. Then P1, say from 5 atmospheres to 10 atmospheres. Please, you may also need to know that it could also be given in Newton per meter square or in Pascal. So you must be able to play with all this. So I will allow the class now to look at example 4, and then example 5. Then we will now go to the other lecture, which is its capacity. Let us see. Now, it says calculate the work done when 1 mole of an ideal gas at 25 degrees Celsius and 5 atmospheres is allowed to expand irreversibly against the constant outside pressure of 1 atmosphere until the internal pressure has been lowered to 1 atmosphere. Now, the initial volume is this. V1 equals nRT over P. And now that we know that we are dealing, Please, you need to note the units units that are being used. We know that V1 equal NRT over P. So we'll do some calculations. Our N we know is equal to 1. Our R in liter atmosphere will be 1.082. The temperature we know that is 298 Kelvin. Then our P1 is 5 atmospheres. So you now calculate it. So our P1 is now 64.5. Then the final volume is larger than what we have. Therefore, we know that our V is inversely proportional to 1 over P. Therefore, we now calculate our V2. So let's look at it again. Calculate the work done when 1 mole of an gas at 25 degrees Celsius and 5 atmosphere is allowed to expand irreversibly against the constant outside pressure of 1 atmosphere until the internal pressure has been lowered to 1 atmosphere. So you need to look at that. You need to look at that. So we know that it is now 5 times larger. It's 5 times. So all you need to do is to multiply by 5, and you have your 322.25. And from there, you do your calculations. We know that our W equals minus P delta V. Therefore, it equals minus P V2 minus V1, which equals 1 atmosphere into 322.5 minus 64.5 liters. And that gives you minus 258 liter atmosphere. I also want you to also work on your own on example 5, which I believe is very simple. Say calculate the work done when 50 grams of an iron reacts with hydrochloric acid in a closed vessel of a fixed volume. Then number 2, an open beaker at 25 degrees Celsius. Now you know that if you say it's a closed volume, it means there is no change in volume. Our dV equals 0. And if you're now multiplying your pressure against 0, it gives you 0. So your W, the work done, when the work done, when 50 grams of iron reacts with hydrochloric acid in a closed vessel will be equal to 0. But in an open beaker, our W equals minus Px delta V, or dV. So then our delta V equals the final volume minus initial volume. And we know also from our equation that equals nRT over Px. Then you now have to you write your equations, your equation of the chemical reactions, and then you balance it. You balance it. And then we know that a mole of iron will give you, molecular weight will give you 55.85 grams per mole. So you do your calculations, and then to get the number of moles, which is N, it will be 50 grams that you are given divided by the molecular weight. Then that is N. Then R is 8.314 joules per mole per Kelvin. Then the temperature is 298 degrees Kelvin. So you know that. So 298 Kelvin, and eventually it gives you 2.2 kilojoules. 2.2 kilojoules. So next class we'll start with our heat capacity. We start with our heat capacity.
So something like that. The unit of the gas constant is 0.08.
So that
Anyone that you want to just do this.
okay. We're done. Mhm. Let's go to another person. Now give me the system. Please go ahead and speak. Hello?
Hello, sir. Good morning,
Please.
sir.
Good morning. How are you?
Fine, sir. Sir, please, I want you to help us check this example 3, where the pressure was increased. You said it's a gas molecule expanded reversibly isothermally from 5 to 10. That's that value. If we should punch it, it will not give us the answer there. I don't know. Maybe I'm the one. So I just want to draw your attention. The value we have, according to the slide, we have minus 3998.
What do you have there?
You
have 3998.
I had minus 1717.3 joules.
Okay. I will look at it. I will get back to you.
Then, sir, again, I was thinking maybe if
just speak up.
Okay. I was thinking maybe if it was expansion, the final pressure should be lower than the initial pressure. But here we moved from 5 a.m. from 5 a.m. to 10 a.m., which implies that the pressure is actually and then the volume should decrease. Sir, isn't that looking like compression?
Yeah. So at any need to change in any of the variables, is either it expands or it compresses. But like you have just asked, I will look at it again and get back to you.
Okay, sir. Thank you very much, sir.
Okay, sir. Yeah. Thank you very much. God bless you. This one. Daniel, please go ahead.
Yes, sir. Good morning, sir.
Good morning.
Yes, sir. The 1.08 to used, how do we get it, sir?
In fact, the liter something. It should be point it should be 0.082, isn't it?
Yes, sir.
Daniel, it should be, I just need it should be.
Okay, sir.
It should be 0. Yeah, it should be. You are very correct. Thank you. God bless you.
Yes, sir.
time.